We have discussed in earlier conversations that soils are inherently nonlinear, non-elastic. And look, here we are talking about linear elasticity. And you may be wondering why. Well, there are many reasons. One is that it is the asymptote at the beginning of all deformation. And if we know that asymptote, and we know the asymptote at failure, then the details in between may not be that critical. Second, because for any process, we can always look at linearization at a given point, like a Taylor expansion. So it could be considered locally linear. Third, because many aspects of mechanics are very stable to the assumptions that we make. So it's not that we are imposing a linear elastic model onto soil behavior. We're just creating a framework to understand soils and to conduct engineering analysis. So what are the equations of mechanics? Let's go back to the analysis of a simple cantilever beam subjected to a force N. Then that is quite easy to understand. It's a system in equilibrium, and so the beam is taking all the force. But now let's make it a little bit more complex. And if we place a spring here, now we wonder how much the deformation will be and who is taking most of the load. And so from equilibrium, we know that the force taken by the beam plus the force taken by the spring is going to be equal to the normal force, but we don't have other equilibrium equations, so we cannot solve it only by equilibrium. Now, we are going to make a very important assumption, that the tip of the beam and the spring are moving together and that there is no discontinuity that emerges. Then we can add one more equation, which is the deformation at the tip of the beam is equal to the deformation that the spring will experience. And now we have the two equations and two unknowns, but they are in different terms. These are forces, these are deformations, and so we need to convert deformation to forces or forces to deformations. And so we need another set of equations. For example, the deformation of the spring will be equal to the force carried by the spring over the spring constant, while the deformation of the beam will be proportional to the force carried at the tip of the beam, carried by the beam, times the length of the beam cube over 3 times the moment, the modulus, times the moment of inertia of the beam. And now, by combining these two equations, I can solve my problem. So the equations of mechanics are equations of equilibrium. In most of our problems, except for a simply supported beam, those are not enough, so we need to impose compatibility among deformations. So these are compatibility equations. But because they are in different terms, we need to combine them, and we need to translate one to the other through constitutive equations. Now we can solve the problem. The question is, what type of physical models are we used to connect deformations to forces? For example, in this case, we are assuming that the spring is linear. And so this is a spring of this form. So this is a linear spring. Now, you can also have progressive springs. For example, a spring of this form, and this is a progressive, and they have very different responses. And we're going to impose that the deformation of the body is going to be linear, in other words, proportional to the force. And why do we require that? Because it opens tremendous opportunities. The reason follows. If we have a linear system, and this is force and this is deformation, and this is the response, so this is the spring constant K, then if I apply a force, F1, I get a deformation delta 1. If I apply twice the force to F1, then I do get a deformation that the deformation for two forces is actually twice much than the first deformation. And that means that I can put them in any order I want and there will be no problems. And so that is one characteristic, but above all, they are additive. For comparison, let's say that I would have a weakening spring, which would be as follows. And so this is force and this is deformation. Now, if I apply first this force 1, I get this deformation 1. If I apply another force 2, so this is the magnitude of F2, I would get this deformation 2. But notice that if I apply F1 plus F2, it will be F3. So this is F1 plus F2. I would get a deformation that goes to infinite and clearly is not equal to delta 1 plus delta 2. So a very important conclusion is that in a linear elastic system, the superposition principle applies. And that is critical. So far, we have this first observation related to the important equations that we need for mechanics. Then we have acknowledged the fact that we are going to go for linear elastic systems. And now we are going to come to the 17th century and part of the 18th century for two important set of parameters. One is by Hooke, and it says that the stress is going to be proportional to the strain, where this is Young's modulus. By the way, Euler had anticipated Young's modulus 80 years earlier, but we give the name of Young's modulus. The other parameter that we are going to need is to recognize that when you load a system or an element and you apply the load, it tends to get shorter and fatter, in such a way that if I compute the strains in the normal direction and the strains in the parallel direction to loading, we recognize that in the direction of loading is experiencing contraction. However, in the normal direction, it tends to experience expansion. So it gets shorter and fatter. The ratio between these two is another parameter from the 19th century from a mathematician, Poisson, and is defined as follows: epsilon in the transverse direction over epsilon in the parallel direction. But because one gets shorter and the other one gets larger, so they have different signs, and we like to work with positive material parameters, by definition, we are going to add the negative sign. What comes next is a combination of strains in different directions, recognizing Poisson's effect, adopting the superposition principle. So now let's explore an element where we are going to subject it to loading in different directions. So let's start. This is sigma z, and it's going to get shorter and fatter, and so epsilon z, according to Hooke's law, is going to be equal to sigma z over E. Now let's apply a horizontal stress. This element is going to get narrower and taller by Poisson effect. So in the horizontal direction, there will be an epsilon x, which is equal to sigma x over Young's modulus. If it is isotropic, the modulus is the same in all directions. Now remember that Poisson's ratio tells us that the strain in the normal direction with respect to the strain in the parallel direction change sign satisfies this ratio, and therefore now the strain in the normal direction is epsilon z, is going to be equal to epsilon x, Poisson negative sign. So epsilon z due to a loading in x is minus Poisson sigma x over E. Now we can extend this further, but imagine that it is a system loaded in 3D. And so now we have a stress coming from the back plane and from the front plane, and this is sigma y. Sigma y is also going to produce a strain in y equal to sigma y over E, and because of Poisson effect, it's going to get narrower in the y direction, taller in the z direction. There will be an epsilon z equal to minus Poisson sigma y over Young's modulus. Because of superposition in this linear system, then we can add the three strain contributions produced by sigma z, sigma x, and sigma y to get that epsilon z is equal to 1 over E, parenthesis, sigma z minus Poisson sigma x plus sigma y. So this is the summation of the strains produced by the 3D state of stress. So this is Hooke's law generalized to 3D. We can do exactly the same for the strains in X and the strain in Y produced by the three states of stresses. An interesting case in linear elasticity is when we have a body that is subjected to state of stresses in three directions, and so it experiences volumetric contraction due to that state of stress. And so the body will expand from an original, or contract from an original smaller dimension to the larger one that occupies now, and we want to compute the volumetric strain it is experiencing. And so volumetric strain, by definition, will be the final volume of the body minus the initial volume divided the initial volume. Let's assume that it was cubical, just to simplify. So this is going to be equal to final volume minus L cubed. Let's say that the original dimension was L, and this is expanding. I could have chosen the other one. And so this is the volume at the end is the length plus the change in the direction x times the length plus the change in the direction y plus the length times plus the dimension change in z minus the L cubed over L cubed. Let's inspect this equation. When we multiply these three pairs, L cubed is going to appear and is going to cancel with this L cubed. When I multiply one with the other, I will have L squared times dz. So let's explore that one. The first one will be an L cubed minus an L cubed over L cubed. Another term will be L squared times delta z. There will be another term, L squared dx, and another term, L squared dy, plus, and then comes the delta x, delta y L, delta x, delta z L, and delta y, delta z L. Now, the deltas are very small, and delta times delta is very, very small. And the last term is delta x times delta y times delta z, and it's very small. Let me explain what we are doing. If you have this change, let's say that this is the body, what we are actually getting rid of is these corners, in fact, aristas that go along the body, which are much smaller than the other ones. So in the end, this is going to take us to delta z L squared plus L squared delta y plus L squared delta or dy's delta x over L cubed, which is equal to delta z over L plus delta y over L plus delta x over L, and these are the three strains. Summary: epsilon volumetric is equal to epsilon x plus epsilon y plus epsilon z if and only if the strains are small, because we're throwing away the corners. The previous definition or computation of the bulk strain allow us to compute the bulk modulus in terms of the volumetric strain and the change in isotropic stress that caused it. And so this is going to be equal to that change divided the volumetric strain, which is the sum of three strains. And let's say that the whole system was under isotropic stress changes. So this is 3 epsilon in any direction, x, y, or z. And that epsilon is equal to the change in isotropic stress over 3 sigma 0 over E. I factor out from Hooke's generalized law, which is 1 minus 2 Poissons. So this was, let's say, sigma z minus Poisson, sigma x plus sigma y, but given the fact that sigma z, sigma x, and sigma y are the same, I can factor them out. And therefore, now this delta sigma 0 cancels with that one, and what I obtain is that the bulk modulus is the Young's modulus over 3, 1 minus 2 Poisson. This modulus will allow us to estimate the volumetric strain the soil mass experience due to the change in isotropic stress. In engineering, we use the shear modulus to relate the shear stress to the shear strain. But let's be precise about this. This assumes that the body is subjected to a shear stress, and therefore it will deform to experience shear deformation like that, where this angle is the shear strain. Well, in reality, that shear stress cannot exist by itself because it creates a couple which violates equilibrium. So as we discussed in the context of Mohr circle, there is a reciprocal couple that emerges when I apply shear stress, and the body actually deforms as follows. And this is what is called the pure shear strain, which we're going to call it epsilon xy. But that is the pure one from mechanics. This is the one we use in engineering. And as you can see from geometry, if I rotate, so it's a shear distortion plus a rotation, I obtain this gamma. Therefore, gamma, the engineering shear strain, is twice the pure shear strain acting on the xy plane. With that in mind, now let's try to obtain a relationship between the shear modulus and Young's modulus, and we're going to do it with this system. This body is going to get shorter and fatter because I'm loading it only in the vertical direction. So if I draw the Mohr circle of stresses in this case, I have that there is tau sigma. I have this Mohr circle of stress where this is sigma z, and there is no horizontal stress. So tau is equal to sigma z over 2. Now we can also draw the Mohr circle for strains, and if we do that, this element experiences an epsilon z, which is from Young's modulus, sigma z over E, but because of Poisson, it experiences a minus Poisson epsilon z. The one I'm plotting here, this is epsilon axial strain, and this is epsilon xy, which is equal to gamma over 2. Therefore, the maximum shear strain, this is gamma over 2 that the system has experienced, is actually this diameter divided by 2, or in other words, this is the engineering strain, which happens to be equal to epsilon z 1 plus, even though it's on the other side, but I'm looking at the whole diameter, Poisson. Now, this quantity here is Young's modulus. Therefore, we conclude that the shear modulus is Young's modulus over 2, 1 plus Poisson. So far, we have talked about an element being loaded in one direction, and that gave us Hooke's law and the generalized Hooke's law. Then we subjected the element to isotropic state of stress, and in this case, we were talking about the bulk modulus. Finally, we subjected the element to shear, and of course, with reciprocity of shear stresses to compute the shear modulus. The next one I would like to extract the equation is the case where the element is subjected to vertical loading, but it cannot, these ones were getting shorter and fatter. This one, the element cannot get fatter because epsilon horizontal is forced to be equal to 0, and that is called the constraint modulus. So let's start by computing what would the strain be in the horizontal direction under a generalized state of stress. Well, epsilon horizontal would be equal to 1 over E, the loading in that horizontal direction, minus the Poisson ratio, the loading in the other horizontal direction. Let's say that this is X and the other one is Y, so the loading in the other horizontal direction plus the loading in the Z direction. Now we are saying that this applies when epsilon horizontal is equal to 0. When epsilon horizontal is equal to 0, then we can multiply both sides by Young's modulus, so that goes out, and I get that sigma horizontal is equal to plus Poisson, because it goes to the other side, sigma horizontal plus Poisson sigma z. Now, if I put the two sigma horizontals to the left, it becomes 1 minus Poisson, and so 1 minus Poisson sigma horizontal is equal to Poisson sigma z, and if I compute sigma horizontal over sigma z, turns out to be Poisson over 1 minus Poisson. And so go back to the previous studies where we were loading the soil vertically under 0 lateral strain, and we had Jackie's equation for the ratio between sigma horizontal and sigma vertical under 0 lateral strain. We call that K naught. And it turns out that the theory of elasticity predicts that K naught is Poisson over 1 minus Poisson's ratio. That is the theoretical estimation under linear elasticity. But let's continue with our goal, and our goal is to compute the constraint modulus, which by definition is going to be the ratio between sigma vertical over epsilon vertical when epsilon horizontal is equal to 0. Therefore, this is sigma z, and epsilon z now is produced by the change in stresses. These are all changes in stresses in the x, y, and z direction. So this is going to be equal to 1 over E, the E goes to the top, sigma z minus 2 Poisson sigma horizontal, and the sigma horizontal is Poisson over 1 minus nu of sigma z. This becomes Young's modulus equal to 1 minus 2 Poisson square, 1 minus Poisson, common denominator, 1 minus Poisson. And this can now be factored out as this is the constraint modulus in terms of Young's modulus and Poisson's ratio. Please notice that when the Poisson's ratio goes to 0.5, this becomes 0, and the constraint modulus goes to infinite. And that raises a question. Let's go back to Poisson's ratio, and what are the values for Poisson's ratio? So if we plot here the values of Poisson, let's say 0, this is 0.5, this is Poisson, then what does Poisson 0.5 mean? Well, let's think of the following system. Imagine a cube that we are going to squeeze vertically, but the medium is totally incompressible. That means that when it gets shorter and fatter, it will go down by epsilon z in the vertical direction, but that volume now will expand into epsilon x and epsilon y, half and half. So that means that for an infinitely stiff material, when the bulk modulus goes to infinite, is so stiff that it cannot experience volumetric changes, then Poisson's ratio is 0.5. So this is the case when the volumetric strain is equal to 0. And of course, you can go back to the definition of volumetric strain, and it will be the same. Now, any material that is between this regime and this regime is actually experiencing volume contraction. And there is a situation that is quite unique, and where could Poisson's ratio exist at values less than 0? What does that mean? It means that you shorten it in the vertical direction, and instead of getting fatter, it gets shorter and narrower. And that's very difficult to conceive, except if you think of a structure that looks, these are all little levers, and so when I squeeze it vertically, the centers go to the middle and everything contracts horizontally. So this is quite unique, and cork is near this regime. Some foams are near this regime. Here are contractive soils and materials, which is most of the materials, and this is when the material actually dilates. So when we think that liquids are incompressible, basically we're assuming that Poisson is 0.5. It's not totally incompressible. Water does compress a little bit, and so Poisson may be 0.495. It's not perfectly 0.5, but it is interesting to recognize that Poisson's ratio is not just 0.3 or a fairly fixed value, that it could be a wide range of Poisson's ratio for our different materials. One of the equations that turns out to be quite valuable is to recognize that the constraint modulus is equal to the bulk modulus that we derived in the previous screen, plus 4/3 the shear modulus. Please convince yourself, go ahead and replace and add up, and you will see that this is the case. And why is it so valuable? Because the bulk modulus is relatively easy to compute, adding the bulk stiffnesses of the different components. The shear modulus is the one that comes from the shear wave velocity, and the constraint modulus m is the one that gives us the p wave velocity, or conversely, by measuring the p wave velocity, I compute the constraint modulus. And so here we see a relationship between the parameters that govern p and s wave propagation in soils, which is of utmost importance for in situ characterization using geophysical methods.